Welcome to another podcast. This episode, we're going to take a look at how to prove a logical equivalence. So I want to list a statement in terms of symbols, Boolean symbols here, and I want us to prove that the statement is logically equivalent to another statement that doesn't look quite as similar. The one that we're going to take a look at today is not P or Q. And we're going to show that that's logically equivalent to the statement not P and not Q. So first off, a couple of points here. The statement with the double bar arrow like this, we're going to use that to stand for logically equivalent. And now the second part to this is, okay, what does logically equivalent mean? Well, logically equivalent means that both statements have the same truth values in all cases. And so the easiest way to do this is by constructing a truth table for each statement and then looking and seeing if the truth table line by line matches up. You can do this as one big truth table, but personally I like to do it using two of them and then just compare. So I'm going to take the statement on the left first. So we're going to look at the statement. So we're going to need P and then Q and then P or Q, and then we're going to have to negate it. So we're going to need basically what I have here. Okay, so let's look at P and Q, then we're going to have to form P or Q, and then we're going to have to negate P or Q. So all possible truth values and then from a previous video, we know how to form the truth table for an OR statement. OR statements are true as long as at least one of the two arguments are true. So it's only false down there at the end. And then we're going to use the negation operator to change the truth values of the previous statement. So this is the truth value for the statement not P or Q. So let me construct another truth table, this time for not P and not Q. This one's going to be a little bit longer because I have to have a column for P, a column for Q, a column for not P, a column for not Q, and then a column for not P and not Q. So just make sure we give ourselves plenty of space here. So P and Q. And then we're going to look at not P, not Q, and then not P and not Q. All right, so both are true, true, false, false, true, both are false. And then let's negate P, so we're negating the first column. So false, false, true, true. And then not Q, we're negating the second column. And then not P and not Q, we're going to do an AND statement between these two columns. So we're going to do AND between those two. So false and false is false, false and true is false. Since it's an AND statement, they both have to be true, which only the last one is. Now what you note is the truth value for this statement matches identically the truth value for this statement. And because of that, these two statements are logically equivalent. Now, this is a special logically equivalent statement known as one of De Morgan's laws. Let me go ahead and write those down. Not P or Q is logically equivalent to not P and not Q. That's the one we proved here. And then the other De Morgan's law is not P and Q is logically equivalent to not P or not Q. So together, these form what are called the De Morgan's laws. basically, if you look at what they're stating, they basically tell you how to distribute a negation symbol. So if you distribute the negation symbol, you have to change the order of operation from an or to an and vice versa. So if you distribute negations, you have to flip an and to an or an or to an and. That's De Morgan's laws. Another set of logically equivalent statements that we'll use all throughout the semester. The first one is called the contrapositive. The contrapositive states that P implies Q is logically equivalent to not Q implies not P. We actually use this as a proof technique sometimes. Sometimes it's easier to assume that the conclusion is false and then show that the preceding value is false as well. So those two statements are logically equivalent. The other one is the biconditional equivalence, and I talked about this in the previous video. The statement P if and only if Q is logically equivalent to P implies Q and Q implies P. So this is called the biconditional equivalence. And so all four of these laws, De Morgan's laws and the contrapositive biconditional equivalence, are four heavily used logical equivalencies throughout the course. And so they're just worth sort of committing to memory that these statements mean the same thing. Because sometimes it's easier to prove one side or the other if it's stated in the other way. All right, so this is how you prove logical equivalences in the course. We're going to use this throughout the semester to build up other logical equivalences, but it's, once again, sort of a soft introduction to this idea. Thank you for watching.